We've got a lot to cover today. This is week 4, and so we're going to dive right into chapter 4 today. Before we do that, I'll take one more little look at the syllabus. I still have a few people emailing in. I've had a few people say, hey, I couldn't even find the website. So anyway, and I guess it's kind of pointless to go through that, but anyway, because if you can't get to the website, I can't show you how to get there because that's where I am right now. But trapped in cyberspace. Yeah. But anyway, here's the syllabus one more time, and I'll just go ahead and show you where we are. We're in week 4, and so last week we finished up chapter 3, and there's just about as many chapters as there are weeks. So if you're kind of lost, like, oh, what chapter are we on? What week is it? You're done. So here we are in week 4. We're going to start chapter 4 today. We're going to finish it on Thursday. It's one of the more important chapters in terms of understanding the physics and really digging down into the types of energy. So there's a lot there, and that's really what I want to focus on today. I have graded the exam. Well, Moodle graded the exam. If you have any additional questions about something that you didn't understand, just shoot me an email. We'll go over it. I see other people are hitting that first problem, and I also have the first problem set posted. It's there. It's not due. It's not due until week 7, but if you want to take a look at it, start playing around with it, I just thought I'd give you a heads up on problem set 1. So hopefully by now you've had a chance to take exam 1. If for some reason you couldn't find the website or whatever, I don't mind cutting you a little bit of slack because I know there's a few people out there that are just kind of still getting used to Moodle. And again, summary 1 is now officially due because it's week 4. It was again the window for submitting summary 1 is now closed. But that said, if your laptop went down or something happened, I will accept summary 1 late as well. But our next task is to get ready for exam 2. Which I will open in 2 days, and which I would like you to complete by 1 week from today. So hopefully the due dates are clear on that. All right. So I'm just going to go ahead and hop into the images.
I just had a quick question.
Oh, yeah, go ahead, Kat. Yeah, for sure. Please.
I'm pretty sure it was on your Moodle page, you have an assignment 1 on there. I was just curious if that was something that we had already done.
No.
Somehow missed it.
No, you did not miss it.
Awesome.
No, summary 1 is due week 7.
Oh, assignment 1.
Yeah,
week
the
7.
problem set 1
Okay,
is due week
gotcha.
7. So you got.
Great.
I figured I'd rather. A lot of times, people come into this course. They're not necessarily math majors. They're not pursuing an engineering degree. Sometimes the math can be a little intimidating. Mm-hmm. That's why we did that example problem class. You got plenty of time to look at it, and that's why I sort of delay that. So it is sitting there for you to look at. If you want to start panicking now, you may, and dig into a little bit. And I'm happy to go over some of those. Some of what we're going to do today in class, I think, will be a big help towards getting that first problem set done because we'll dig into some of the mathematics and the engineering and the physics.
The only other thing was
Yeah.
when you submit summary 1,
Mm-hmm.
the submission portal thing that I went and clicked on didn't actually give me an option. So I posted it in the discussion.
That's good to know.
Summary 1 forum.
Okay, you should definitely post it in the forum. And
Exactly.
okay, super. And then if the portal wasn't open, I apologize. Peter McDonough is fixing all of that. I put him in charge of updating all of the due dates. So
Okay.
yeah.
I did that quiz 1 and it was like 300 and something days late.
Yeah, that was,
Yeah.
I was like, what?
yeah, it was kind of weird. I don't know why.
I was like, man.
Yeah,
I'm like,
yeah.
no, it's not late.
No,
so.
it's not. It's not. Yeah, and I'm sorry. I mean, nothing's perfect.
Oh, it's all good.
Me and Moodle included.
Oh, but this noodle is weird itself. Little creature.
Yeah, it really is. So hopefully that's clear. The problem set 1 is not due until week 7, and we will get that portal open. Okay, so there are 25 figures in this chapter. I'm going to try to get through at least 12 or 13 of them today. I'm going to try to get through at least half of them. So I'll try to cover half the chapter today.
This is a big chapter too. Chapter 4.
Chapter 4,
Yeah,
yep.
It's a big section.
It's a big one. It's a big one, and it starts off pretty big. There's a picture of Isaac Newton himself. Doesn't get a whole lot bigger than that. So the three things we really want to take a look at here are Newton's 3 laws. One thing worth noting is that Newton stole 2 of the laws from Galileo. So the first one is that, hey there, the first one is that objects in motion tend to stay in motion, and basically that just means, and I'll just write it like this: the change in velocity equals 0. So delta v equals 0. It just means that if I throw something up into outer space, it's just going to kind of keep going on forever. And in a sense, that's similar to the conservation of energy. It means unless something affects that thing, it's going to maintain its energy. It's also going to maintain its momentum.
What does it equal right there? Is that a 0?
That's a 0.
Okay, I didn't know if that was a
Yeah.
theta or something.
So delta v, change in velocity equals 0 is one way to think of it. Objects in motion stay in motion. The second one is that the sum of all forces equals 0. And the easiest way to think about that is, just I'm standing on the ground and I'm pushing on the table with the same force that the table's pushing on me. And so that's more one of the first laws of statics. If you go into engineering, there's a whole course on statics, and all you're doing is adding things up that come to 0 all day long. It's also the equation that civil engineers rely upon. You go and look at the Golden Gate Bridge. It's not moving. That's a good thing. It's because all the forces sum up to 0. So that's the second law.
Can you say it again?
The sum of the forces equals 0. So that's a sigma. So the sum of the forces equal 0. The sum of the forces equals 0. The first law is that the change in velocity equals 0, or objects in motion tend to stay in motion. Second one is the sum of the forces equals 0. And then the third law is the one you've probably heard of. It's as famous as Einstein's equation. It's just that force equals mass times acceleration. And that's the one I want to focus on the most here. And force equals mass times acceleration. And that's just the famous apple experiment. The apple falls, the earth is pulling on that apple or that pen with the force, and it accelerates. The velocity is not 0. The longer it falls, the faster it goes, as long as that force is pulling. Now Newton's big breakthrough, his big thought experiment. Well, I'm sitting here on Earth, the apple falls, it hits the ground. Well, why wouldn't it be the same thing that the moon, soaring around the Earth, feels that same pull? And his thought experiment was, well, let's go somewhere in between an apple that's falling straight down and the moon that just seems to keep going sideways. What's in between those two things? He said, well, if I fire a bullet, that away, with enough energy, it will come back around and hit me in the back of the head. Because, the Earth is round. So at some point, and that bullet is falling, and his big breakthrough, well, the moon is constantly falling. I think it is. Yeah, it actually, I don't know.
No, it's moving out.
It actually is still moving out
Yeah.
at this point because of the initial momentum when the moon was formed from a collision between some other object. and the proto-Earth, and there it goes. So,
Does it get closer and further on an epicycle?
yeah, it does. Its orbit is
The orbit
And it
is
depends on-
oblong or?
yeah, it's elliptical.
Depends on where we're tilted too.
Right. So it's not quite that simple, but force equals mass times acceleration. Now, those are the symbols. And another thing I want to take you through here are units and dimensions. So force has, we've talked about the fact that energy has units of joules, power has units of watts, force has the unit of newtons. And what we're going to try to do is figure out its dimensions. So we know that mass has the unit of kilogram. We're well familiar with that. Now, what I'm going to do over here in this dimensions column is just write out a big M for mass, because we know that anything that has a mass we can measure in kilograms, you can measure it in grams, you can also measure it in pounds of mass, or stones, or slugs. There's all kinds of different masses out there. But the dimension of mass is just M. Now, acceleration, we know, is measured in meters per second squared. Now, the dimensions of acceleration, I'll just write it in here, acceleration. The units of acceleration are length over time squared, because meters are measured, well, it's a dimension of length, how long is something, and seconds are the dimension of time. Now, we know that when we multiply mass times acceleration, so this is mass, and this is force. We know when we multiply mass times acceleration, we get force, so the dimensions of the newton, which is a dimension or a unit of force, has to be just ml over t squared by simple algebra. Okay. Now we know exactly what the dimensions of force are. You can measure it in newtons. You can also measure it in pounds. You can measure it in dynes. There are all other types of units of force, but there's only, really, this is the only sort of dimension of force, the fundamental dimension of force. There are ways to tie that in with electrical force and coulombs and things like that. We're not going to worry about that too much for now. So now what we're going to do is tie force in with power and energy. Very important. Okay, so energy equals force times distance. So, for example, if I'm going to do some work, I'm just going to take this pen and move it. I'm going to take it from here, and I'm going to move it here. That took energy. I applied a horizontal force. There's also a vertical force acting on that pen, so I had to overcome, from gravity. I had to overcome that. And if I multiply the amount of force I just applied, very small amount, multiply that by how far I moved it, that's how much energy it took. It's that simple. It's that simple. So energy is force times distance. Power equals force times velocity. So again, I'll just do this very simple, very simple experiment where I could either, if I'm not very powerful, imagine I'm an ant. I mean, maybe I've got a good strength to weight ratio, but if I put a little ant harness on this thing, the ants, the ant harness, the little ant colony will be able to move this this pen eventually, but it's going to take a while because the ant is not very powerful, right? So, but if I very quickly do it with my finger, you can imagine me brushing away an ant, I did it more quickly, so I was more powerful. So, same amount of energy, and we did that. Remember when we had the energy was that rectangle under the,
The
under
one
the
you're
line.
squared on the sun, or on the earth,
What's that?
the one you're squared on the earth, is the one you're talking about, the equation? How much sunlight the 1 meter earth gets?
No, we're not talking about radiation.
Oh.
No. No, we're just talking about mechanical energy and power right now. Yeah. The one I was referring to is where we had, this is time, and this is power, and we did these little energy rectangles.
Okay.
Yeah, those rectangles.
Okay.
Yeah.
Sorry.
No problem. So now we can look at the dimensions of energy. So we know from our previous slide that force is mass times length over time squared. Now, distance, obviously, has dimensions of length, so we just square it. We'll do it this way. Times length equals mass length squared over time squared. Okay, so mass times length squared over time squared, those are the dimensions of energy. Now for power, we're just going to multiply force over length over time squared. Velocity is meters per second, miles per hour. Distance divided by time, length divided by time. So from there we just get ml squared over t cubed. So those are the two fundamental dimensions of. And once you know that about energy and power, you know a lot, because then whenever you're solving an equation, you'll be able to dig back and say, oh, is this a force equation I'm working with? Is it an energy equation? Is it a power equation? So there we go. Any questions on that? So we've kind of covered Newton's three laws. We've gone over the units and dimensions of force, mass, and acceleration, which is his third law. He stole the first two from Galileo and put this third one out there. And this really led to the invention of calculus, because as it turns out, you don't need to know this, but as it turns out, velocity just equals, actually you do need to know this. It won't be on the test, but every human on Earth over the age of, I don't know, a certain age should know this. Velocity is the change in distance over the change in time, and acceleration is the change in velocity over the change in time. And then Newton took it one step further and said this just equals d dot. The dot just means the change, and then acceleration just equals v dot. And this equals d double dot. And we won't get into that, but those are the symbols that he invented 300 years ago to explain how things move throughout the universe. And once you've got those derivatives, you can go back and do integrals. And as it turns out, this little figure that I drew here is an example of an integral. And basically what it shows you is that energy equals the integral of power over some change in time. So this is a little change in time right here, a delta t, and all of this stuff in here is energy. Okay, so that's Newton. Sir Isaac. Another way to think of this, I did the little pen experiment a second ago. I did it horizontally. I can also do it vertically. And so in order to get the pen from here to here, I had to push on it. I had to, and again, the force was vertical, and so was the distance. And if I multiply the force times the distance, that's the energy. Also worth noting that, also very critical, energy and work same dimensions. And it's similar to saying, well, how tall is something? Well, you can measure it in meters. How wide is something? You can measure it in meters. How thick is something? You can measure it in meters. So height, length, and width, and distance, they all have the same dimension. Distance, length. And same thing with energy and work. They're also measured in joules. So energy and work mean very specific things in physics. It's just measured in joules. Okay. Typically, though, when we're talking about work, we'll go back to this one little example. When we talk about work, in order to push this pen along, the energy of the pen really did not change. It's not any higher or lower than it was. If it fell off the table, there you go. If I attach that to a pulley, I could then do something, pump some water or move something. So if I do this, where'd the energy go? I mean, you saw the thing move, but it doesn't really have any more energy than it did a second ago. Where'd the energy go? It's just yeah, exactly. It just turned to heat. If I pushed it really hard, you might actually hear it. That energy came off as acoustics, but all it did was just vibrate the air in the room. But if we had a thermal camera, we could come down here and look and say, oh, there's a little heat signature left. The pen got a little hotter. The table got a little hotter. The energy didn't go anywhere. So I did this work on the pen, but it all just turned into heat. Yeah.
It can also take a minuscule amount of mass away from the pen, which is really hard to do.
Maybe, yeah. That's a fascinating thing to think about. Yeah, of turning some of the mass into radiation. Yeah, we didn't quite go nuclear, but yeah, that's true. E equals mc squared. We'll get there. Okay. Okay, so there's Newton, there's energy, there's work. Okay, so what the authors are gearing us up for is how we might calculate the energy in the wind. And we've seen this already with summary 1. I tried to show the energy density. We did a few problems on last week on looking at radiation density. And when you look at this problem, you can say, oh gosh, look at this. So I don't have photons flying at that wind turbine at the speed of light. I just have air molecules flying at it at, what do they give for the problem here? How fast is that wind going? Oh, 9 meters per second. 9 meters per second. So let's just run through this problem really quick here.
What page is it in the book?
I'm on page 116. Page 116. Yeah. Let's go through this guy really quick. And I'm going to skip having you, do follow along and write this down as I go through it, but I'm going to skip sort of the problem. I'm going to skip having you work this on your own. Okay, so the question is, how much power does the wind deliver to a turbine with a diameter of 60 meters when the wind speed is 9 meters per second, about 20 miles per hour? So I'm just going to cut right to the chase here and go through the problem. So what they're doing, this is very similar to what we did before. So here's the turbine. Here's the wind. And so really what we need to do is look at the volume. What's the volume of this cylinder of wind that's approaching the turbine? So the diameter is 60 meters. So this is the diameter, top to bottom. And so therefore the radius is 30 meters. And so we now know that the volume, and really what we're looking at, so really what we're looking at is how much wind actually goes through this thing in 1 second. So the wind is blowing at 9 meters per second. And so we know that this 9-meter long chunk of wind is going to go through that turbine in 1 second. So the volume of this wind that goes through, the volume just equals the length or the height of the cylinder times pi times r squared. And r, of course, is just 1/2 d. Plugging in the numbers, we get 9 times pi times 30 squared, and of course the 30 comes because it's just half of the diameter, equals 25,447 cubic meters. Pretty big. It's a big wind turbine. Same type of turbine you'd see up on the High Line. So 25,447 cubic meters. Now, we need to know what the mass is, right? Because we go back up here to energy and power, knowing the mass is critical. So, in order to get that, we just know that the mass equals the density of air. That's a rho. Looks like a little p, but it's a rho. There's no tail on it. The density times the volume. The density of air is 1.29 kilograms per meter cubed. That's the density. We'll multiply that by the 25,447 cubic meters. So the meters cubed will cancel, and we'll be left with kilograms. So at the end of the day, we've got 32,827 kilograms of air coming at the turbine. And then the authors say 32 tons of air coming at the turbine. It's a pretty good chunk of air. Okay.
Would
So-
you say that's per second?
Yes, you would. That's exactly what you say. 32,827 kilograms of air moving through the turbine per second. That's exactly right. So what we want to know is what's the energy of that? So the energy equals 1/2 m, the mass, times the velocity, so that's a little v squared. And then the power, what we're going to go with here, the power just equals 1/2 the, let me see here, 1/2 the times the mass, which we already got. Yeah, and this is how they get away with this. 1/2 times the velocity squared, which is 9. Right. Squared, and this is how we'll do it. Yeah, per time. This is not the conventional way to do it, but it works for this particular system. So we know that energy equals 1/2 mv squared, and if we go back, let's just take a look at the dimensions on that. So there's your mass. You got length squared divided by time squared. So that works out. And this is kinetic energy. This is energy moving. So then we know that this is happening every 1 second. So from there, it's just a matter of saying we got 1/2 times the 32,827 kilograms that we looked at already, times the 9 meters per second squared. And as Kat, as you pointed out, that happens every second. And then just run those numbers, we're looking at 1.33 megawatts of power. That's a pretty standard sized turbine, you know, a 1 to 3 megawatt system. Okay, so we just did our first energy and power equation for a renewable energy system. Now, all of that energy is not going to be converted directly into electricity. There's a thing called Bett's law that prevents some of it from actually being converted. We'll get into that when you take Energy 242. Okay, so let's just take a break there, unless there's any questions. So that's kinetic energy.
Can you go up just a little bit?
Oh, sure. Yeah. Yeah. So we started out, just to review it, the diameter of the turbine was 60 meters. We needed to know the volume of that chunk of air traveling through the turbine. We know that volume is the length times pi times r squared. So the length of the air moving through it was 9 meters, and that happens, as we decided, every second, times pi times 30 squared, which is our velocity, or I'm sorry, which is our radius. We came up with a volume of air of 25,447 meters cubed. We multiplied that by the density and decided there's almost 33 tons of air moving through. Yep.
So right there on that equation, when you did the mass equals
Density?
you said that's not a P times.
That's a rho. That's the letter rho.
Rho, so
Yep.
it's a Greek letter.
Greek
What
letter
does that
rho.
stand for us?
It's density.
Density?
Yeah.
Okay.
Mm-hmm.
Thank you.
Rho is the conventional letter for density.
Okay.
So M equals rho V. I think, I don't know if the author uses rho or not. They just say the density is, they just state what it is. Yep,
I just
yep.
make sure I have that.
Yep, yep, yep. And then the units cancel, you're left with kilograms. We know that the one form of energy is kinetic energy, and that's the equation for kinetic energy, 1/2 mv squared. And then we know that power is energy divided by time, and that much energy passes through the turbine every second. And so we can now see that, yeah, we've got the dimensions of power are kilograms, which is mass, meters squared, and then we've got seconds squared in the denominator, and then a third second squared in the denominator. So we can also say that a watt equals 1 kilogram times 1 meter squared divided by 1 second cubed. That's also those are the units, the fundamental units of the watt for mechanical energy. 1 watt equals 1 kilogram times 1 meter squared divided by 1 second cubed.
What did you call it?
These are the fundamental units of the watt.
Okay.
The mechanical, for a mechanical watt. We'll get into an electrical watt here in a little bit, probably next week, or next lecture. Okay, let's just take a break now.